Welcome to the Security Buddy. Today we will discuss the mathematics for quantum computing from vector space to Hilbert space. Let's start our discussion with vector space. Before we learn quantum vectors or qubits, let's ask a fundamental question. What kind of numbers are we allowed to use in quantum computing? In computer science, we use various data types such as integers, floats, and booleans. For quantum computing, we need a mathematical structure where arithmetic such as addition, subtraction, multiplication, and most importantly, division work perfectly. In mathematics for quantum computing, this mathematical structure is a field. Now, let's try to understand field. A field is a set of numbers equipped with two operations, addition and multiplication. To qualify as a field, the set of numbers must obey certain rules. Number 1. Closure. If we take any two numbers in the field and add or multiply them, the result must still be in the field. Number 2. Identity. There must be an identity element for addition and multiplication. And number 3. Inverses. Every number in the field must have an inverse. So, let's look at some examples and non-examples of fields. The set of integers is not a field. If we take the integer 5 for example, its multiplicative inverse is 0.2, which is not an integer. It breaks closure. The set of real numbers is a field. We can add, subtract, multiply and divide real numbers and the results stay in the field of real numbers. The set of complex numbers is also a field. Arithmetic like addition, subtraction, multiplication and division works perfectly in the field of complex numbers. For quantum computing, we select the field of complex numbers. But why do we do so? Let's try to understand that. The real numbers form a perfectly valid field, but real numbers are not enough for quantum computing. In quantum mechanics, probabilities are calculated from amplitudes, and these amplitudes have both a magnitude and a phase. Because of this, quantum computing chooses the field of complex numbers. Every vector space we build for quantum computing is built over the complex field C. This allows quantum interference, where states can cancel each other out, much like physical waves. So, what is a vector space? In quantum mechanics, a vector is an object that obeys a specific set of rules when we add it to another object or multiply it by a number from the field. A vector space is the collection of all such possible objects. It requires two fundamental operations to exist. These two operations are vector addition and scalar multiplication. If we take two vectors in quantum computing and add them together, we should be able to get a new vector. This is the mathematical foundation of quantum superposition. On the other hand, if we take a vector in quantum computing and multiply it by a scalar, we should be able to get a scaled vector. This is how we apply probability amplitudes to our quantum states. So, let's look at the axioms. Closure. If we add two vectors in the vector space or scale a vector by a complex number, the result must be inside the same vector space. There is a null vector which, when added to another vector, keeps that vector unchanged. Please note that an empty vector is not the qubit state K0. It's rather a null or empty vector. Inverses. For every vector, there must be an inverse vector. And distributivity. If we scale a combined vector, it should be the same as scaling the vectors individually. So, let's look at an example. Let's consider the complex two-dimensional vector space. Here, K2 and Kv are two vectors in the vector space and alpha 1, alpha 2, beta 1, beta 2 are complex numbers. We can perform a vector addition and scalar multiplication to create a superposition of K2 and Kv. Let's look at the inverses of K2 and Kv. Please note that the null vector is not the same as K0. So, what's next? We have defined a vector space, but we don't yet know how to measure the distance between two vectors, how many dimensions a vector space has, and whether two vectors are perpendicular to each other. We are going to discuss these topics in the next section. We can take a set of vectors from a vector space, scale each one by a scalar and add them all together. For example, let's say K2 and Kv are two vectors from the vector space. We can multiply the vector K2 by the scalar alpha and Kv by the scalar beta and add them together to create a superposition of K2 and Kv. Here we are taking a linear combination of the vectors K2 and Kv. So, what is a span? The span of a set of vectors is the collection of every single vector we can possibly create by changing the weights alpha and beta in the linear combination. For example, the span of the vectors K0 and K1 is the entire single qubit vector space over the two-dimensional field of complex numbers. By varying the complex numbers alpha and beta, we can reach every valid single qubit state in the vector space. A set of vectors is linearly independent if none of the vectors in the set can be written as a linear combination of the others. If we have three vectors and the third vector can be built by adding the first two vectors together, then the third vector is redundant. The third vector in this case does not expand the span. It is redundant. The states K0 and K1 are completely independent. One can multiply K0 by any complex number, but one will never turn it into K1. K0 and K1 point in entirely different algebraic directions. What is a basis? A basis is a minimal, non-redundant set of vectors that completely spans a vector space. To be a basis, a set of vectors must satisfy two strict conditions. They are, they must be linearly independent and they must span the entire vector space. For example, in quantum computing, the following vectors are called computational bases. Please note that K0 and K1 are linearly independent and K0 and K1 span the entire vector space over the field of complex numbers. However, please note that a basis is not unique. We can always choose a different basis to describe the same vector space. For example, the following vectors form a different basis in the same vector space over the two-dimensional field of complex numbers. As we can see, these two vectors are linearly independent and they span the entire vector space. So, what is a dimension? The dimension of a vector space is the number of vectors present in its basis. If a space requires exactly two basis vectors to span it without redundancy, it is a two-dimensional space. However, please note the following. One qubit lives in a two-dimensional space. Two qubits live in a four-dimensional space and n qubits live in a 2 to the power n dimensional space. So, by the time one has 300 entangled qubits, the dimension of the vector space is 2 to the power 300, which is more dimensions than there are atoms in the observable universe. So, why do we need Dirac notation? In standard linear algebra, we use bold letters for vectors and complex matrix notation for operations on these vectors. Massive columns and rows of complex numbers every time we want to calculate a qubit state gets messy at times. In 1939, physicist Paul Dirac invented a syntax specifically designed to handle the calculations of quantum mechanics. It is called bracket notation. So, what is a kth vector? A kth is a column vector and it is written as kth psi. A vertical bar on the left, an angled bracket on the right, and it encloses a label. For example, K0 and K1 are written like the following. Similarly, a bra is a row vector that is the conjugate transpose of the corresponding kth vector. It is written as an angle bracket on the left, a vertical bar on the right, and it encloses a label. What happens when we multiply a row vector or a bra by a column vector or a kth? In matrix algebra, we get a scalar. In Dirac notation, we specify the scalar like the following. Please note that if the scalar is 0, then bra phi and ket psi are perpendicular to each other. Now, let's discuss inner product. We know what a vector space is and how to create a superposition of vectors in a vector space. But we do not know the lengths of the vectors and the angle between them. In the classical world, we use the standard dot product to find these angles and lengths. In the quantum world, we use the inner product. In Dirac notation, the inner product of bra phi and ket psi is written like the following. So, what is the norm of a vector? If we visualize a vector as an arrow, then we may want to know how long is that arrow. In standard geometry, we use the Pythagorean theorem to find the length. In quantum mechanics, we use a generalized version of this concept and we call it the norm. The norm is a function that takes a vector and returns its absolute mathematical magnitude. Let's say ket psi is a vector in our vector space. To find the square of the norm, we take the inner product of the vector with itself. And to get the norm, we take the square root. Here is an example. So, let's discuss the three laws of a valid norm. Number 1 is positivity. The norm of a vector ket psi is always positive and it is exactly 0 only when the vector is an empty vector. Number 2 is homogeneity. If we scale a vector ket psi by a complex number c, then the norm of the vector scales by the absolute value of that number. And number 3 is triangle inequality. The norm of two vectors ket psi and ket phi added together is always less than or equal to the sum of their individual lengths. Why is the norm of a vector in quantum computing always 1? In pure mathematics, a vector can be of any length it wants to be. But in quantum computing, we have a strict physical constraint called normalization. Let's say ket psi is equal to alpha ket 0 plus beta ket 1. As per the Born rule, when we measure a qubit, the probability of it collapsing into ket 0 is mod alpha square and the probability of collapsing into ket 1 is mod beta square. As the total probability of all possible outcomes must always equal exactly 1, we have mod alpha square plus mod beta square is equal to 1. This implies that every valid physical quantum state vector ket psi must have a norm of exactly 1. These vectors are called unit vectors. If a quantum gate or environmental noise accidentally changes the norm of a state vector, say from point 8 to 1.2, the probabilities break, and that does not make any sense. What if we put the ket before the bra? We call it the outer product. In Dirac notation, the outer product of ket psi and bra phi is written like the following. In Dirac notation, an outer product represents a linear operator that transforms one vector into another. So, we have discussed vector space and Dirac notation. Our next topic is linear operators. Why do we need linear operators? In a classical computer, we pass bits through logic gates like AND, OR, NOT to change their states. In a quantum computer, we pass our ket vectors through linear operators. Mathematically, we can think of an operator as a function. We feed it a vector, it processes it, and outputs a transformed vector. An operator T is called a linear operator if it obeys the following rules. We can also combine the above rules together and write as follows. As operators are linear, if we know exactly what an operator does to the basis states ket0 and ket1, we automatically know what it does to any superposition state in the universe. We only need to distribute the operator to each component. In finite dimensional quantum spaces, every linear operator can be written as a square matrix. If we are working with a single qubit, a linear operator is a 2 by 2 matrix of complex numbers. Let's say bra phi is a bra vector and ket psi is a ket vector. The outer product of these vectors creates a matrix and is a linear operator. Let's say ket u is another ket vector. As we know, the inner product of bra phi and ket u is a scalar. So, the operator here effectively takes the input ket u, measures how much it overlaps with bra phi and uses that result to scale the vector ket psi. Let's look at an example of linear operator. Let's say ket psi is a ket vector. The identity operator I operates on any vector ket psi and leaves it unchanged. So, how linear operators are related to quantum gates? In quantum computing, every quantum gate can be represented by a linear operator. The linear operator corresponding to any quantum gate is a unitary operator. These unitary operators rotate and evolve the qubits without changing their overall length. Thus, they ensure that the total probability remains 100%. Now we are going to discuss metric space. Why do we need a metric space? We now know that qubits live in a vector space and we can use inner products to check if they are perpendicular. But if we want to measure limits, errors, or how close a quantum state is to a target state, we need a rigorous way to measure distance. In mathematics, any space equipped with a strict rule for measuring distances is called a metric space. A metric is an abstract function that calculates the distance between two elements from a metric space. A metric takes two inputs and outputs a single real number representing how far apart the inputs are. Let's define a metric. A metric is a function usually denoted as dxy that takes two elements from a space and maps them to a real number. To be a valid metric, this function must satisfy four golden rules. In mathematics, any space equipped with a strict rule for measuring distances is called a metric space. The four golden rules that a valid metric must satisfy are: 1. Non-negativity. The distance between two elements can never be negative. That is, dxy is greater than equal to 0. Number 2. The distance between two elements is exactly 0 if and only if they are the exact same point. That is, dxy is equal to 0 if and only if x is equal to y. Number 3 is symmetry. The distance from element A to element B is the same as the distance from B to A. That is, dxy is equal to dyx. And number 4 is triangle inequality. The direct distance between two elements is always the least. In other words, if we take a detour through a third element, the distance can only get longer or stay equal. We have already discussed how to calculate the norm of a vector in a vector space. In quantum computing, the distance between two vectors kt and kv is the norm of their difference. In quantum computing, states decohere and drift due to environmental noise. A metric allows us to mathematically quantify how much an error state has drifted away from the ideal target state. If the distance is small enough, the error correcting codes can correct it. Thus, metrics lay the groundwork for concepts such as quantum fidelity and trace distance, which engineers use to benchmark the accuracy of a quantum computer's hardware gates. Now that we have discussed a metric space, we can measure distances, track errors, and quantify how close vectors are. This ability to measure distance enables us to generate infinite sequence of vectors that move toward a specific limit. But what happens if that limit does not exist inside our space? To fix that, we need to discuss Cauchy sequences and completeness. This is the final missing puzzle pieces that turn a standard space into a Hilbert space. Let's discuss convergence of vectors. A sequence of vectors converges to a limit vector ket if, as we progress, the distance between the vectors in the sequence and the target vector ket reduces to absolute zero. To say a sequence converges, we must already know what the target vector is. But what if we are exploring a new space and don't know the target? This is where the Cauchy sequence becomes important. So, what is a Cauchy sequence? A sequence of vectors is a Cauchy sequence if the vectors get closer to each other when we progress. Is every Cauchy sequence a convergent sequence? A sequence is a Cauchy sequence if the terms of the sequence get closer together when we progress through the sequence. However, such a sequence may or may not converge to a specific limit. For example, the sequence may converge to a limit that is excluded from the space. Let's consider the following sequence of rational numbers. As n increases, the terms get closer together and hence the sequence is a Cauchy sequence. But e is not a rational number. The sequence is a Cauchy sequence but not a convergent sequence. Now, let's discuss what a complete metric space is. If every Cauchy sequence in a metric space converges to a valid limit, the metric space is called complete. If a Cauchy sequence clusters together but its final limit is outside the metric space is incomplete. In quantum computing, we frequently use infinite series, continuous time evolutions, and limit operations to design algorithms and simulate error drift. If our vector space were not complete, we could run a perfectly valid quantum algorithm where the states get closer and closer to a final answer, but the final limit state would mathematically vanish as it lies outside the space. Completeness guarantees that the limits of the quantum states are always valid quantum states. Now let's discuss Banach space. We have discovered that a space needs to be complete. We need to ensure that the space has absolutely no mathematical holes and all tightly clustered sequences have a valid destination. If we take a standard vector space, give it a norm and ensure that it is entirely complete, then we have created a Banach space. The Banach space is named after the Polish mathematician Stefan Banach. Now Let's define the Banach space. A space is qualified as a Banach space if it satisfies the following. Number 1, it is a vector space so that one can add and scale vectors. Number 2, it is a normed space so that every vector has a well-defined length. Number 3, it is complete such that every Cauchy sequence of vectors converges to a limit that is also inside the space. There are certain limitations of Banach space. Banach spaces are incredibly powerful, but they have a limitation when it comes to quantum physics. A Banach space knows how long a vector is, but it does not have an inherent concept of angles. It does not know if two vectors are perpendicular. In quantum computing, we don't care about the length of a state vector alone. We also care about orthogonality. And to get these angles, we need to upgrade our Banach space one last time. Now, let's discuss Hilbert space. So, how do we introduce angles and perpendicularity to a complete Banach space? We equip it with the inner product that we discussed earlier. When we take a Banach space and define its norm using an inner product, we unlock geometry. We can now calculate lengths, limits, and angles without any structural holes. A Hilbert space is simply a Banach space with a geometric superpower, the inner product. So, a Hilbert space is an inner product space that is also a complete metric space. It is named after David Hilbert, one of the most influential mathematicians of the 20th century. Now, let's define a Hilbert space. A space is a Hilbert space if it satisfies the following four criteria. Number 1, it is a vector space over a field. For quantum computing, the field is the complex field. Number 2, it has an inner product which also provides a norm and a metric. Number 3, the inner product allows us to define angles and strict orthonormality. And number 4, it is complete. Every Cauchy sequence of quantum states converges to a limit that lives inside the same space. In pure quantum mechanics, particle positions and momenta are continuous. This requires an infinite dimensional Hilbert space, where checking for completeness is incredibly difficult and strictly necessary. But in quantum computing, we work with discrete qubits. A single qubit lives in a two-dimensional space, and an n qubit system lives in a 2 to the power n dimensional space. These spaces are finite dimensional and they are complete. Now, let's bring everything all together. The superposition is just a linear combination of vectors. The phase and interference are managed by the complex numbers in our field. The quantum gates are unitary operators that rotate our vectors in the Hilbert space without altering their lengths. The measurement outcomes are projective transformations that collapse our vectors onto the orthonormal basis axis with the probabilities dictated by the vector's norm. If you made this far, you have mastered the core foundational math of the quantum age. If you enjoyed this deep dive, make sure to hit that subscribe button, and I will see you next time on the Security Buddy. Thank you.